So let's suppose I'm collecting a sample of size n, where n is a relatively large number, so around 30 or greater, and my specific variable of interest in this case is continuous. So for the purpose of this example, we'll suppose that I'm measuring the heights. So for each person in my sample, I'll collect their height. Well, in that case, where my variable is continuous and my sample is relatively large, if I were to graph it and visualize it, more often than not, it can be pretty well approximated by a normal distribution. It won't be exactly a normal distribution, but it would be approximately the same, where I have some mean and I'll have some variance or standard deviation. Now in most cases, for our sample, our standard deviation is denoted by the letter S, but if our sample is large enough, S is going to equal the standard deviation of the entire population, or be very close, and that would be represented by sigma. Now in that case, one of the things I may be interested in is what is the proportion of people within the sample, and by extension the population, that fit in some interval of data points. So if I'm interested in heights, let's say my average height was 1.8 meters, and I was interested in what proportion of people fit between 1.7 meters and 2.0 meters. And one of the tools that we can use to make this problem really easy is z-scores, since proportions and probabilities go hand in hand. Before we get to z-scores, we're going to look at a specific rule that we can apply to all normal distributions, or approximately normal distributions, that are relatively symmetric and not too skewed. So if we have a relatively normal distribution, excluding skewed distributions, so we're assuming symmetric, then we have three intervals where we pretty much know the proportions right away. And this is just a basic specific case of using z-scores. So our first interval is our mean plus or minus one standard deviation. So that would be starting at our mean minus one standard deviation, going all the way to our mean plus one standard deviation, which is essentially two standard deviations in width. This interval, according to the empirical rule, contains 68% of all data points. And so the probability that you select a random person and they fit within one standard deviation of the mean is approximately 68%. If we keep going and look at an interval where we add or subtract two standard deviations, so x minus two standard deviations or x plus two standard deviations, so now our width is 4 standard deviations, this interval contains approximately 95% of all points. Finally, if we consider the interval where we add or subtract plus or minus 3 standard deviations, so now our interval is going to be 6 standard deviations in size. This interval contains 99.7% of all data points. So if we visualize this, let's suppose that one standard deviation is represented by these two green marks. So this is plus 1 standard deviation, or this minus rather. This is plus 1 standard deviation. The area under the curve over here would represent 68% of all the points for both the sample and presumably, if the sample is good enough, for the population as well. If we extend it to 2 standard deviations, we're looking at 95% of all data points, and if we go as far as 3 standard deviations, we're looking at 99.7% of all data points, essentially your entire range. And that's why if a data point lies beyond 3 standard deviations, aka your data point has a z-score that's absolute value is greater than 3, so it's less than negative 3 or greater than 3, in that case your data point has a lower chance of being selected than 0.3%, and in that case it should be considered an outlier. So now we have an example where we can use the empirical rule. We have the heights of grade 12 students being normally distributed And so right away we have validation that we can use the empirical rule since our distribution is going to be normal. The distribution has a mean of 1.6 meters and a standard deviation of 0.4 meters, and we want to know with what confidence we can say that a randomly selected student would fall between 1.2 meters and 2.0 meters. So you could solve this problem with z-scores. However, it's specifically made to be solved with the empirical rule. It turns out that the numbers work out nicely. And so we'll start by defining our random variable. So we'll say let x be the height of the students. And in that case, x is a normal variable with a mean of 1.6 meters and a standard deviation of 0.4 meters. What we'll notice is that our interval of 1.2 meters all the way to 2 meters is the same thing as our mean of 1.6 meters minus our standard deviation up to our mean plus our standard deviation of 0.4 meters. So essentially this is the first interval we saw where we had x bar minus sigma and x bar plus sigma, or x bar plus or minus sigma. And if you recall, this interval contained around 68% of all data points. Now, randomly selecting a student from the population or from the sample is essentially a trial within an experiment. And the probability of the event of it landing between 1.2 meters to 2 meters, if you remember from continuous distributions, that probability would be 68%. And so to answer this question, we would say, therefore, we are around 68% confident that a randomly selected student would lie, or would have a height between 1.2 meters to 2.0 meters. And that's essentially the same thing as saying that the probability that our random variable is greater than or equal to 1.2 meters or less than or equal to 2.0 meters is equal to 0.68. Alright, now we don't want to limit ourselves to 3 possible intervals. Instead, we'd like to have any interval and know the percentage likelihood that a value is going to be within that interval, or the proportion of values that are within that interval. And that's where confidence intervals come in. And they're called confidence intervals because you can be X% confident, depending on the interval, you can be X% confident that a random value will lie within that interval. For example, if I had a 95% confidence interval, the area under the curve for that 95% confidence interval will be 0.95, and so the probability or the confidence that a value is within that interval is 95%. So you can imagine that we have a normal distribution, and we're going to be using z-scores right now, and so we're going to be considering a standard normal distribution, and then we'll shift back to the x world for the general case. So right now, our goal is to create some interval where inside we know the area under the curve, we know the percent, and we have 2 tails on the side. So we're going to go an equal distance above the mean and an equal distance below the mean. So we have 2 tails or 2 cutoff regions. That's why we're calling this a 2-tailed confidence interval. Now the way we're going to do this is we're going to say we have an area of A over 2. A over 2 below some cutoff region. So we'll call this cutoff, it's going to be a Z value. And we'll call the Z value ZA over 2, since it has an area of A over 2 below it. And since the Z value is below the value of 0, since this is a standard normal distribution, it's going to be negative. So the area, or more specifically the probability that any Z value is less than our Z value of negative ZA over 2, that's equal to A over 2. In the same way, we're going to have another z value where the area above that z value, or the probability that we get another z value above this z value, is also a over 2. And it turns out that this z value is simply the positive version of our negative za over 2. So this is going to be positive za over 2. In other words, the probability that our z is greater than or equal to positive za over 2 is equal to a over 2 as well. So just as an example, and you can check this yourself, if we said that za over 2 is equal to positive or negative 2.34, then the probability that z is less than or equal to negative 2.34 is equal to 0.01, and you can check that for yourself using a z-score table. And just as we showed before, the probability that z is greater than or equal to positive 2.34 is also equal to 0.01. So now, what we know is that the middle region, or this orange region, since the entire area under our normal distribution, which is a probability distribution, since the entire area is equal to 1, since it represents the sample space, then the area in orange, or the probability that z is between, so it's greater than negative za over 2, but less than or equal to positive za over 2, that's going to equal 1 minus our blue regions. So 1 minus a over 2 for the lower tail, minus another a over 2 for the upper tail. And so this is going to be 1 minus a. And that's how you create a 1 minus a times 100% confidence interval. So a is going to be a decimal. You multiply whatever this is by 100%, and you'll get the percentage confidence that a random value is going to be within that interval. So to construct a 1 minus a times 100% confidence interval, that's essentially saying you're going to go from negative za over 2 all the way to za over 2. And as an example, let's say I wanted to create a 95% confidence interval. So I want this area to be 95%. Then that means 1 minus alpha is equal to 0.95. So alpha is equal to 0.05. Half of alpha, or a over 2, is equal to 0.025. And that means that z alpha over 2, the z value that has an area of 0.025 below it and above it, well, that's simply 1.96. And so the interval, in terms of z-scores, the interval that contains 95% of all data points would be negative 1.96 all the way to positive 1.96. Now to extend this, to be able to use it with x values, we remember that the z-score is equal to x minus the mean divided by the standard deviation. And so to express x in terms of z, we can isolate x will equal z times the standard deviation plus the mean. And so if we use that inside our interval, we get that the 1 minus a times 100% confidence interval for x is the mean plus or minus z alpha over 2 times the standard deviation. And if you want that in interval format, it comes out to the mean minus z times a over 2 times the standard deviation plus, or all the way to, the mean plus za over 2 times the standard deviation. So this interval will contain 1 minus a times 100% of all points, and you can control the percent by controlling what a is. So in some cases, we might only be interested in whether a value is below a certain point or above a certain point. So if we have our two distributions, in one case we might only care that our value is below some x and how likely or how confident would we be that it's below some x value. And in the other case, we might be asking the question, or how confident we are that it's above a certain value. This is not a mean. So in one case, we're looking at the confidence below or a lower tail interval, and in the other case, we're looking at the confidence above or an upper tail interval. So in the below case, we'll have our mean plus, now all we need is that this tail has an area of alpha, and so this region has a 1 minus a area. And so in the first case, we'd have a mean plus z alpha, not alpha over 2, times the standard deviation. And in the second case, we'd have a value that is below 0, so it would be the mean minus z alpha times the standard deviation. So the probability that any x value is below this number is 1 minus alpha times 100%. And the probability that any x value is above this upper tail value is going to be also 1 minus alpha percent. And this will be more clear once we do an example. So here's an example that will hopefully clarify things. We have a company that manufactures bolts with a mean diameter of 2 inches and a standard deviation of 0.1 inches. And part A of the question asks us to find and interpret a 95% confidence interval for the diameter of a randomly selected bolt. So first of all, we're going to assume that the data is normally distributed so that we can actually solve the question with our theory behind confidence intervals. Then we're going to say that x is the diameter of the bolt in inches. So in part A, we want to find a 95% confidence interval. In other words, we want to find some range of values where we're 95% confident, or where it's 95% likely that a randomly selected bolt will have a diameter within this range. And the question doesn't specify an upper bound or a lower bound where we care that our interval is below a certain value or above a certain value. And so by default, we'll use a two-tailed interval. So for part A, we remember that a 1 minus a times 100% confidence interval has the form of the mean plus or minus z a over 2 times the standard deviation. Now in this case, we want a 95% confidence interval, and so 1 minus a is going to equal 0.95. Isolating for a makes it equal 0.05, and since it's a two-tailed interval, we divide it by 2, and it's equal to 0.025. Using our z-score table, we'll find that the value of z a over 2, which is equal to z 0.025, so you'll go along the z-score table, look for an area of 0.025, and you'll find that the number, or the actual z-score for this area, is 1.96 in magnitude. And so that's the absolute value. So our z-scores are actually plus or minus 1.96. So the area below negative 1.96 is going to be 0.025, and the area above positive 1.96 is going to be 0.025. And so our 95% confidence interval is going to be our mean plus or minus 1.96 times our standard deviation. So subbing our values in, we'll have our mean of 2 inches plus or minus 1.96 times 0.1 inches, and that comes out to 2 plus or minus 0.196 inches, and in interval notation, that is a diameter of 1.804 all the way to 2.196 inches. And so it's 95% likely, and that means we're 95% confident. Therefore, we are 95% confident that a random bolt will have a diameter between 1.804 inches to 2.196 inches. And it's always really important to write that therefore statement included with your confidence level. So in this case, that's 95%, letting the reader know or giving them context about your answer. Now in part B, we're asked to find or verify for the company that at least 95% of the bolts are less than 2.2 inches. We want to know if that's true. So we have our distribution for the diameter of the bolts, where this is our mean, so it's not 0, it's our mean of 2 inches. We have some value, an upper bound. We want to know if at least 95% of all points are below this value. And that value happens to be 2.2 inches. And so in this case, we're using a one-tailed interval where our tail has an area of A above it. So the lower tail, or the orange region, has an area of 1 minus A. And we require that this area of 1 minus A is equal to 0.95. And so if you remember, our equation for a lower tail confidence interval, or 1 minus A times 100% lower confidence interval, was all the points that are less than the value of the mean plus Z sub A times the standard deviation. So since 1 minus A equals 0.95, aka the orange region is 0.95, then A is equal to 0.05, and you'll know that Z sub A, which is equal to Z 0.5, or the Z value with an area of 0.5 below it, turns out that there's two values that we could use. We have 0.0 or 0.0505, and we have 0.0495. This corresponds to a z-score of negative 1.64. This corresponds to a z-score of negative 1.65. We're interested in 0.05, which is in between both these values, and so we'll average them to get a z-score of negative 1.645. And so the z-score, or the area, below the z-score of negative 1.645 equals 0.05. Likewise, the area above a z-score of positive 1.645 is also equal to 0.05. So our confidence interval is going to be our mean plus or minus 1.645 plus the standard deviation, which is equal to 2 inches plus or minus 1.645 times 0.1 inches, which is equal to 2.1645 inches. Therefore, we are 95% confident that the value of a bolt is, or the diameter of a bolt is below 2.1645 inches in diameter. That value is less than 2.2 inches, and therefore we can verify the company's statement in question.